It is part 2 of section 16.4, Generalization of Corinth Theorem. Corinth Theorem is proved for vector field F defined in simple regions. Here we'll extend it to the cases where D is either a finite union of simple regions or having holes. Look at the figure. It shows two images, two regions having a hole each. For these regions, we may cut the region, or we may cut twice, here and here. Then we can separate the region into D1 and D2, two subregions. For this figure, for example, consider the double integral. Double integral over the q sub x minus p sub y. That can be done with this d1 and d2 and separately, and we can add the values. Now, if we consider, for example, d1, then d1 itself is a simple region, so we can apply the Corinth theorem. Also for D2, we can apply Corinth theorem. So for D1, the boundary of D1 is this. Here for C6 and C1 and C5 and C2, these four parts the boundary of D1. For D2, we have here C4, and this is already C6, so that this is minus C6, and C3, and minus C5. These are the boundary of D2. Now, if we try to evaluate the line integral piece by piece, then from here we have C5, and we have another integral with a C5, but now is negative direction, to reverse direction, minus C5, so that after addition, this integration, that reverse direction integration will be cancelled. The same way, here this will be cancelled, so that eventually the boundary of D1 and D2 are the same as that boundary and this boundary. This will be cancelled here again, along with the cut, the boundary integration will be cancelled. So here we can conclude the observation in this way. Double integral over D having a hole, q sub x minus p sub y, can be obtained through this line integral p dx q dy. In this case, the boundary of D is the collection of all boundaries of D. So here, for this region, this is boundary, positive oriented, because if you walk along this portion, then you can see left-hand side, the region. And this is a positive orientation because you can see left-hand side, the region, so that these two portions are the boundary of this whole D, right? So we can get such a formula. Now we summarize our observation. That is the generalized Corinth theorem. Let D be either a finite union of simply connected regions or of holes, of which the boundary is finite and oriented. If the vector field F has continuous partial derivatives on an open region including D, then we have this equation satisfied. That is generalized Green's formula. Line integral positive oriented for every boundary. P dx q dy is the same as region integral over d q sub x minus p sub y. Here again we say round d is the boundary of d positively oriented. Okay, let's try to solve this problem. Evaluate the line integral where C is the boundary of the region between two circles. One is a circle of radius 2 and the other one is a circle of radius 3 having the positive orientation. Okay, so pictorially you can see the region in this way. One is circle of radius 2 and the other one is circle of radius 3 in xy plane. So it's 2 and 3. So here positive orientation means this one, and now inside, for inside the circle, direction must be this one, and these are two circles are boundary and region D is between these two circles. So that is D, and collection of these two is the boundary. Okay. Now, so that the given integral is same as region integral over D, and we are using this formula q sub x minus p sub y. That's q. X derivative will be 3x squared and minus, okay, now for this one we apply y derivative, then that will be minus 3y squared, right, and dA. So that will be 3 times x squared plus y squared. So we may write here 3 out of the integral is constant, and this is x squared plus y squared and dA. So if we evaluate this regional integral, then we're done, right? Now D is a polar region. Okay, so we are using polar coordinates. 3, the angle is from 0 to 2 pi, whole circulation, and R is moving from 2 to 3. Radius 2, radius 3, right? And the integrand is R squared, and we need a scaling factor R, and dr d theta. Okay, here it is separable, or we can say theta independent, so that we can get the theta integral easily. That is 2 pi, and this is r cubed, and antiderivative of this one is 1 over 4 r to the 4, and here we have to get evaluation from 2 to 3. Right? Okay, so this first portion is now, okay, that is along with this quarter, that is a 3 over 2, so that 3 pi over 2, that's the coefficient, and this one, that is 81 minus 16. You can simplify. Okay, that's the final answer. Okay. Okay. Here we have a vector field. F of xy is PQ. P is this one, and Q is that. Then, once xy is not the origin, then Q sub x minus P sub y can be calculated or computed in this way so that it is 0, which means that except the origin, this one is conservative, q sub x equals p sub y, so that the integral is 0 for any simple closed path that does not pass through or enclose the origin. So the far away the origin, the curve is, closed curve is considered, then inside the vector field is now differentiable, and so that also it is conservative, so it must be 0. Okay, we already know that. Here in earlier we found that, okay, conservativeness is equivalent to integral, line integral is 0 for every closed curve. Right? Closed curve. Right? And then also it is independent of path. Okay, the path. And here mathematically also it is same as that q sub x is same as p sub y, but that one is the same when the domain we are dealing with is simply connected, and over the whole domain the partial derivatives are continuous. But once the origin is not enclosed inside of a curve, then everywhere we have this equality satisfied, so that now for closed curve and the integration must be 0, right? We already know that. Okay, what if we have a curve, closed curve, enclosing the origin? We consider the same vector field as in the above example. Then, now here, the line integral of the vector field is 2 pi for any positively oriented simple closed curve that encloses the origin. So here, the case is, right now, we consider a closed curve, and that is positively oriented, but now the origin is inside of this closed curve. For that, for any choice of closed curve, the problem is asking us to show that the line integral is 2 pi. But for this one, we cannot use Green's theorem, because here at one point, now this one has no continuous partial derivatives. Even at this point, this vector field is not defined. So we cannot use the Green's theorem. So that we have to work on a little bit to figure out that the integral is 2 pi. Okay? But we can use the generalized Green's theorem. In order to do that, we introduce another curve, which is C prime, that is a circle of radius a for small a. Once origin is inside this closed curve, then we may have a circle of radius a. A circle of radius a. Of course, in this case, now that C prime is defined in this way, positively oriented. Then, now we consider this region, that one, outside of the circle and inside the original curve. That is D. Then boundary, because for this one we can use the generalized Green's theorem. So that here, that is now boundary integral of the vector field, which must be now C is a boundary that is positive oriented. Now C prime itself is positive oriented. However, as the boundary of D is negatively oriented, so we have put here negation. We have to consider the reverse directional integration. So these two will be the boundary of the region. Okay, one is C, the other one is C minus C prime. Okay. Now, so that we reach this one, and in this case, and we can use the generalized Green theorem, because everywhere in this region it has continuous partial derivatives, and now q sub x minus p sub y is 0, already we know from here. So that is 0, which means that this one, that one, one is negation of the other. Now, along with this negation coming out, we conclude that integral along C, positive oriented, and integral along C prime of the vector field must be the same. So we get this conclusion. Now, we'll try to evaluate this one by using the technique we learned earlier, and we try to get the representation. Then there must be here a cosine t, a sine t. We are using the same A here used to indicate the radius, and t is moving from 0 to 2 pi. Then now integral over C prime f dr is the same as from 0 to 2 pi following the parameterization f of r and r prime dt. If you try to use this one and then here use the vector field, then easily you can see that x squared plus y squared is a squared. So we have here bottom a squared, and you can get here on the top minus y, which is same as minus a sine t. Okay, we can see quite easily. Now from this one, integral from 0 to 2 pi, let's see some detail. Okay, that one is now first component is a squared, and top is okay, that's minus y, right? There's minus y and there's x. Okay, minus y, there is minus a sine t. And the second one is a squared, and x is a cosine t, right? And then here r prime t, r prime, there is minus a sine t, and prime is a cosine t, and dt. Now this dot product will make here, that is a squared sine squared, that is exactly this one, plus a squared cosine squared, that is this one, and we have a bottom a squared. So that here, and we have that. Now, this whole thing is the same as 1. Cosine sine squared plus cosine squared is 1, and the quotient is a squared. We have a squared in the bottom, so that this whole thing is 1. Integral from 0 to 2 pi, the integral in this 1, so that we can get 2 pi, right? So this result is true for arbitrary curve enclosing the origin. So for arbitrary curve C, we can get all A's. here such the circle, and we excluded this circle and we can consider the region D, and we can apply the generalized Green theorem, and we can reach at here this integral, and that integral is the same. But for that integral, for all a is all raised to pi, so that eventually the line integral for arbitrary closed curve, the evaluation is the same as all raised to pi, right? Okay, so we proved that. Okay, now go to new problem. Evaluate line integral closed curve y squared dx plus 3xy dy, where C is the boundary of the semi-annual region D in the upper half plane between the circles x squared plus y squared 1 and x squared plus y squared equals 4. Okay, let's see the domain and curve. Okay, we have x-axis and the y-axis and upper half plane and radius 1 and radius 2. And this is region D, and the curve is that positive direction, like that, and going this direction, and then moving that direction. This is curve, and inside is region D. Okay, we want to get that one. Now we can use the standard Green theorem. So given integral is same as regional integral over D, and then now for this Q we make x derivative, then which is 3y, and minus for P we apply y derivative Q sub x minus P sub y, right? That's 2y, and dA. Okay, that's y, and so we rewrite here integral over D and y dA. Now the region is a polar region, so its angle is from 0 to pi, and radius is from 1 to 2. Y is r cosine theta, r sine theta, I'm sorry. And always in polar coordinate, x is r cosine theta, y is r sine theta, right? And then we have to put another r for scaling factor in this change of variable, and the theta. Okay, lower bound, upper bound are constants, and these are separable. So we separate 0 to pi for sine theta, and for r integration from 1 to 2 r squared dr, right? Okay, for this first portion, and that is 2. So antiderivative is minus sine theta, and evaluation to pi is 1, and now and at 0, so the minus 1, so that must be 2. So this quantity is 2, and that one will be 1/3 of r cubed, and from 1 to 2. That will make 8. This is 8, okay, 7. So that 14/3. That's the final answer, right? Okay, here we summarize what we have learned. For line integral along the boundary, round D, and positive oriented, P dx Q dy is the same as the regional integral of Q sub x minus P sub y. That formula is applicable when these two are satisfied, the boundary of D is finite and oriented. The boundary must be oriented. Okay, let's go back to the problem here. For this one, right now, if you are considering only the curve or closed curve enclosing the origin, then this point, if we try to exclude only this one point, okay, think a figure again. It's a little bit confusing because we have extra curve. Now that is a curve C, okay. So that is at the point, it is not differentiable, so that if we exclude this point, then you may think that excluding this point, this is a kind of region having hole. But for that one single point, it is not orientable. A point can be, at this point, you may look at either this direction or that direction, so that a point, that one, we don't have any orientation. So that's reason here we try to make another circle and exclude this region, and so that the boundary can be oriented. A single point is not oriented, so you cannot use the standard Green theorem for this problem. Okay. So the boundary must be oriented, and the vector field has continuous partial derivatives over the whole region there. So once the quality of vector field is good enough and the boundary is finite and oriented, then you can use this formula always without any doubt. Okay. Okay. For these problems, now you can solve quite easily. Exactly same technique you can apply. And for this one again, this is one example of Green theorem using this formula, and boundary of the region must be positive oriented, so that that direction, that direction, that direction, that direction, x dy, there's no change in y, so that along this boundary must be 0. Along this portion, x is 4, y change is 2, so that you will have 8. And that one, there's no y change is flat, so that you will have a 0 contribution from these two portions. And for this last one, you will have to parameterize, start from here and end here, so that r of t can be 1 minus t, and the point, start point is 2 and 2, and the point is 0 and 0. Okay. Of course, t is between 0 and 1. That's the parameterization. Let's say there is a fourth component, C4, 1, 2, 3, 4. Okay. Now, for this one, so we can write that as 2 minus 2t, and again 2 minus 2t. Right? So here, now the integral and C4 and x dy, that is, now x is, okay, the t is moving from 0 to 1, x is 2 minus 2t, and y, dy is y prime, which is minus 2, and dt. Right? Okay. So there is a minus 2 comes out, and antiderivative of this one is now 2t minus t squared. And we are evaluating from 0 to 1. Right? So that is minus 2, and that is 2, and this is 1. 2 minus 1, So we have minus 1. Okay, no, minus 2. So we have here that is minus 2. So all addition is 6. Okay, the region, the area of the region is 6. You can see it quite easily. So part by part along the boundary, you can get the line integral and sum. Another way you can get the final answer quite easily is here. So for that one, is related to the issue, main idea in your project. So midpoint of x and change in y. Midpoint of x is the 2, change in y is 0. So we have 0. Midpoint of x from here to there is 4, and change in y is 2, so that a. So midpoint of x is 3, change in y is 0, so that's 0. Midpoint of x is 1, okay, so that 1 times change in y, which is minus 2, from 2 to 0, so that minus 2, so we have minus 2. So by using this numerical technique, you can get it much more easily, okay? Either way, you can do it. Okay, that's the end of the section. Thank you.